immediately after our return from Texas, after the car was safe and secured in Seattle, we hosted a team gathering to celebrate and reflect. We recorded the insights and experiences of many different team members before they left for college and thanked them for all their hard work. The class of 2019 formed the Green Energy team, and they finished their last year very strong. We were eager to keep their momentum going. One of the first questions we addressed was whether to build a new car for the 2020 challenge or to improve upon the car we had previously built. We are very proud of that car, but there are so many places where we could improve. Our team was always up for a challenge, and that's why we chose to build a new car for the 2020 challenge, planning to break our own record. Here's our story.
Now that we had the luxury of a 2019 car as a failsafe, there was much more space to explore, prototype, and research potential improvements. Last year's experience and reflection led us to a few core design philosophies that we agreed upon very early in the stages of the car. The first was that anyone on the team with a license could drive the car at the competition. The second was an emphasis on efficiency. There were two main body styles that we considered: a catamaran style, or a single central body. Our research phase approached these designs with an eye on aerodynamic efficiency, stability, and ease of manufacturing. To accomplish the first value of accommodating all team members, our car would need to adjust to the driver's height and proportions. The mock pit was really our groundwork to reach that value. It was simple and cheap enough to change our prototype quickly, but having a physical model was incredibly useful for ensuring legality within the rules and feasibility to manufacture. Our core value of improved efficiency meant we needed to spend more time researching and crafting the aerodynamics of our design. For a while, we had been intrigued by the possibility of computational fluid dynamics as a design tool. So during the research phases, we tapped into our network for advice from our Boeing engineers. They encouraged us to utilize the tools at our disposal, but always validate the computer output with practical testing and previous research. Our network of engineers also helped us investigate different building materials and techniques. We learned a lot about what goes into the design of a composite structure, and were fortunate to get our hands on quite a bit of it. This early part of the year was also full of learning general engineering skills. We introduced many new students to electronic design, welding, machining, CAD, and programming. We want students to find the area that excites them the most, and giving members the freedom to work on any project is an important method of letting them explore. Our research phase ended with a few key deliberations. We chose the catamaran design because it offered greater stability and ease of manufacturing. While there was some promise of the single body, its main fault was the difficulty of quickly and safely getting the driver out without stepping on the solar array surrounding them.
Our design looks a lot different. We've learned so much and we're excited to try something a bit new this year. We've changed to a four-wheel symmetrical drivetrain and brought down the solar panels to shoulder height. The added wheel forced us to rethink our steering column, as now we must turn two front wheels rather than just one to meet the competition's steering radius regulations. Our solution is an optimally placed bar linkage connecting the two front wheel suspension systems that allow us to implement an Ackerman steering system to meet the competition requirement. Bringing the solar array down to shoulder height has the trade-off of creating shading from the cockpit. If left unchecked, shading can significantly lower our power, dissipating current as heat, which could lead to damaged cells or even fires on the car. We had to redesign the solar array to fit the shade of the canopy and provide connection points for current to bypass any shaded cell. Something we underestimated last year was the number of wires that accumulated in our car. Messy wiring not only slows down our maintenance of the car, but is also dangerous. This year we spent a lot of time planning our wiring by using 2D CAD to create electrical schematics. We've used these schematics to build a central electrical board that is equipped with most of all of our connections, relays, capacitors, etc. We've also looked to improve the safety of the car by isolating high voltage to a smaller section, and no high voltage wires will pass through the driver's cockpit. Another one of our greatest efforts this year was a complete redesign of the telemetry system, using a custom Arduino instead of last year's approach, which used an off-the-shelf product. Instead of transmitting data over a cellular network this year, we are now sending it through a radio frequency and logging it at our base camp. As this is an endurance race, we have to look at reducing drag as much as possible. This is important because drag increases by velocity squared, and the power needed to overcome drag force is proportional to the cube of the velocity. This means that if we go twice as fast, the drag forces would quadruple. To reduce our drag, we have been designing an aerodynamic shell for the car to encase the entirety of all the systems using different computational flow dynamic software, which will make a more aerodynamic design.
This year, our team has been working to redesign our telemetry and data acquisition system. We are collecting upwards of 70 data points all throughout the car, including values such as motor temperature, solar panel current, battery voltage, etc. We are now experimenting with the best method to send those data points from the car to a strategist computer off-field. We so far have tested using Arduino and radio frequency, Raspberry Pi with Python script. We have also experimented with sending the data with internet and with no internet connection. Our goal is to create a system that a strategist could use to visualize all of our data points and then communicate back to the driver about what they should do to maximize energy efficiency and speed of the car throughout the race so that we can drive as consistently and predictably as possible.
We started our fundraising journey with a team-directed letter writing campaign. In order to broadcast our voice to a wider audience, we used our website to keep our supporters informed about the progress of our team. Collectively, we produced monthly blogs that highlighted the accomplishments and milestones of our team. During the year, we organized multiple events and presented our team's mission to the Racebike Aviation High School PTSA auction, the Highline School District, T-Zero Racing, and the Royal Aeronautical Society's Seattle chapter.
As the COVID-19 outbreak emerged, Washington State was the first to shut down all schools and non-essential businesses in the nation. In anticipation of distance learning, we packed everything in our school workshop and transported to our mentor Dr. Sumay's workshop until further notice. The team adjusted remotely while King County was in Phase 1. We quickly discovered that structural progress on the car was not possible as members were isolated from each other and the chassis. In response, our focus shifted to independent projects of electronic and telemetry systems. Weekly, we continued team Zoom meetings. This gives us a space to reconnect with teammates, share our progress, setbacks, questions, and future projections. While we were isolated from each other, the key to continuing progress from home was maintaining efficient group communication. When King County proceeded to Phase 2, the team could finally arrange to meet in small groups to work on the car. There was a huge learning curve as we learned how to social distance, wear face masks, frequently wash our hands, wipe equipment down, and work in ventilated workspaces. We have made great progress, but as we remain in Stage 2, we still do not have access to our school workshop. So, we intend to continue meeting up at Dr. Sumay's workshop as much as we can to continue making progress on the car.